这个米可以看，就这个上页，这个应该是到上页放过了，放过了，就是这个的。按这个回的是吧？So we can see that the fossil energy resource will be exhausted and also cause the serious greenhouse problem like the global warming and the environment deterioration. And so the energy crisis make human to seek for the high efficient and environment friendly energy source, and also giving birth to the global revolution of energy and the environment. So we are developing the sustainable energy resource and clean, renewable. And so since the first discovery of the cold fusion reported in 1969, so also it has not been evidenced solid yet, but cold fusion also initiates efforts in the following, three topics, like the, oh, sorry. Like the highly hydrated metals, calorimetry and the extreme conditions are also no energy nuclear reactions. So I think we agree that the highly hydrated metals is the first step of cold fusion, because it will provide an abundant hydrogen source for cold fusion, and also for the hydrogen storage, catalysis, sensing. So the typical material is like the palladium hydride. So there are only two states of the hydrogen atoms in palladium crystal. One is the surface diffusion of the hydrogen atoms. This is called the alpha phase hydrogen, and the another is the beta phase. So the beta phase is actually the hydrogen atoms was occupied in the 90s of palladium crystal. So the interaction between them is actually the chemical bond. This is much stronger than the interaction in the alpha phase. In this phase is actually the adsorption bond. So this is the electrochemistry of the palladium nanoparticles carried by glassy carbon electrode in a 0.5 molar sulfuric acid solution. So we can see in the whole cyclic voltammetry, and we can see that the small peak just shown in in the right line. This is the alpha phase hydrogen, and the second peak is the beta phase hydrogen. And after that, if the potential goes negatively, we can see that the hydrogen evolution on the palladium nanoparticles. So then rather than in the left, in left figure was shown in the right, we can see that the very clear, the fine voltammetric peaks of the alpha phase hydrogen. So we just forget the oxygen desorption and adsorption in the positive potential range. So here we can see that there is some problem for to get the high density hydrogen the palladium hydride, because we can see that from the left figure we can see that the current of the hydrogen atoms adsorbed on the palladium surface is keep decreasing when the scanning goes on. So indicating that the surface passivation of palladium. And we can see in the figures on the right, we can see that in actually the right one is the palladium before the experiment. That means that no surface passivation. And the blue line is the the same electrode, then after the surface passivation, we can see that the hydrogen insertion to the palladium leaves more negative potential, and also the current decreased. So we can see, and this is actually caused by the structure, the phase change and the structure collapse of the palladium nanoparticles. So this is not good for the high density accommodation of palladium to hydrogen. So my question is that is the palladium is the best choice for cold fusion? So I think the challenge comes from the following three domains. Is stoichiometric number X should be higher than 0.875. So this is very difficult because the structure, unstability, and also the surface passivation and the structure collapse hindered the increase of X, and also the strong interaction between palladium and hydrogen. That means palladium hydrogen bond is the energy carrier that should be overcome for the further fusion. So my primary source is can we just deposit the atomic hydrogen with high density on the other materials? And on this material, there is no surface passivation or structure collapse, and also to weaken the interaction between the hydrogen and its container. So the experiment design is we want to deposit the hydrogen on graphene, and in this system, the hydrogen bond should be the absorption bond. This is much weaker than the chemical bond, and the theoretical hydrogen over the carbon ratio is almost 1. So how to deposit hydrogen on graphene? So the first is the chemical routine. They use the hydrogen as the precursor. So the hydrogen was dissociated. The hydrogen dissociate on the catalysis to form the atomic hydrogen atoms. So these atoms can spill over from the catalyst to the graphene surface and then absorbed on the graphene through surface diffusion. So the challenge in the solid gas environment is that you have to use hydrogen as the resource. And also this process should be performed at a very low temperature and with a very high pressure. This is conflict in kinetics. So we are electrochemists, so we use electrochemistry. When we use electrochemistry, we can use protons as the precursor. So the protons is actually reduced electrochemically by the platinum catalysis to form the hydrogen atoms. So the atoms spill over from platinum to the graphene and then resident there. So this experiment can be totally performed at room temperature with 1 atm pressure. So this is the experiment. So we can see in the right figure, we can see the blue line. So this blue line was performed in the 0.5 molar sulfuric acid with the electrode, the PET-supported single-layer graphene electrode. So we can see that there's no reaction in the whole potential region. So that means the protons cannot be reduced electrochemically directly on graphene. So we can see in the blue line is actually the PET-supported platinum wire. We can see that a very clear hydrogen region in almost in a lower potential. We can see this is actually the protons was reduced to hydrogen atoms on platinum. So if we just composite the platinum wire on the PET-supported single-layer graphene, so with this electrode, we can see that the behavior, the cyclic voltammetric behavior dramatically changed. So had seen that a very big stripping current, which increasing with the scanning and successive scan. So the stripping charge is much higher than the hydrogen absorption capacity on platinum surface, indicating that the hydrogen atoms spill over from platinum to the graphene surface. So we can also we perform the experiment when the surface was activated completely. We can perform the experiment with cyclic voltammetry or also potential step. So we can find that for the cyclic voltammetry, we can find that the peak current, the stripping peak current is in proportion to the scanning square root of the scanning rate. And for the potential step in the transient state, we can see that the integral charge was in proportion to the square root of time. So we can see that this is typically the diffusion process in electrochemistry. And we can from the integral charge, the linear relationship between the integral charge and the square root of scanning rate, and also the square root of the time. So we can just figure out the diffusion coefficient of the surface diffusion of hydrogen atoms on the graphene. We can see that it's so fast. It's at the order of 10 to minus 5 square centimeter per second. This is a very fast diffusion coefficient, also indicating the weak interaction between the carbon and the hydrogen atoms. And from the Arrhenius formed the equation, we can perform the experiment at different temperature from the surface diffusion, the logarithm of the diffusion coefficient with the reciprocal of the temperature. We can figure out the Gibbs energy of the surface diffusion. This is very small, like 21 kilojoule per mole. So this value is very lower than the hydrogen, than the carbon-hydrogen bond. So this is also evidence that is actually an absorption bond. And we also do the experiment with deuterium substitution experiment. We can see that from the Raman, Raman structures in the right figure, we can see that for the pristine graphene, we can see that there is no peak lower than the wavelength of 500. So we can, if we deposit the hydrogen on the graphene, we can observe the sp3, the sp3 peak and in 1352, and also a new peak in 1194. So if we just replace the hydrogen with the deuterium, we can find the new peak at the 863. So this is actually evidence that the carbon-hydrogen adsorption bond. So we also can measure how much hydrogen can absorb on the graphene. So we can just perform the cyclic voltammetry and also the potential step experiment. So we can from the maximum of the stripping charge, we can calculate that the X can be easily higher than 0.8. So this is the main conclusions and perspective. We evidence that both the hydrogen and the deuterium can be electrodeposited on graphene by using protons and deuterium ions as the precursors at ambient environment. So the preliminary study show that the hydrogen carbon atomic ratio is can be higher than 80%, 80%, very close to the theoretical value of 100%. And carbon hydrogen and the carbon deuterium absorption bond are weaker than the metal hydrogen chemical bond, which might be easier for the occurrence of cold fusion. I would like to thank my students and my assistant to perform the experiment and also the valuable discussion and the valuable advices. And thanks for your attention very much. Welcome to visit us at Xiamen University.
Thank you. Thank you, Professor Zhan. Now, question and answer time. 怎么结束啊？看不到那个结束。没有问题就可以结束了。Okay, if anyone have question, you can connect to Professor Zhan. He doing his excellent work. Thank you again, Professor Zhan.
Thank you.